Right now in the Netherlands, you can drive a car directly underneath a lake while a sailboat glides silently above your head, and the boat's crew has absolutely no idea a car just passed beneath them, because at this exact spot, 25 meters separate two completely different worlds, water above, road below, a boat sailing, and a car driving through the same physical space at the same moment, and neither one ever has to stop for the other, not once, not ever. And if that sounds like something engineers dreamed up purely for spectacle, understand this: it exists. Because 3 meters of open lake water sitting directly above moving traffic solved a genuine 30-year-long transportation nightmare for 400,000 people. And the only thing separating that lake from the cars driving beneath it is a single carefully engineered wall. Before this structure existed, the only way to reach the mainland from the Dutch province of Flevoland was a single road crossing a narrow channel. And that channel was spanned by exactly one drawbridge, meaning every single time a sailboat needed to pass through, that drawbridge had to rise, and traffic on both sides simply had to stop and wait. And during peak summer sailing season, a boat needing passage arrived roughly every 20 minutes, each closure holding up traffic for a stretch of time that multiplied across an entire single sailboat. Passage could delay 28,000 vehicles for 15 minutes at a stretch, a disruption that repeated itself every single day for 3 consecutive decades, producing morning traffic jams that regularly began building before 8 o'clock. Flevoland itself is a genuinely remarkable place before you even consider its traffic problems, because the land the province sits on was still open lake seabed as recently as 1968, reclaimed from the water and settled so rapidly that its population had already grown to 400,000 people by 1998, all of them dependent on that same single road and that same single unreliable drawbridge as their only fixed connection back to the rest of the country. Engineers involved in the earliest feasibility studies later admitted that when the original aqueduct sketch first circulated among colleagues back in 1990, many treated the entire idea as something closer to a joke than a serious infrastructure proposal, since nobody working in Dutch civil engineering at the time had ever built anything quite like it, and it took years of careful modeling and repeated presentations before the concept was taken seriously enough to reach formal government review at all. Faced with that recurring daily disaster, Dutch engineers systematically worked through every conventional solution available to them, and each one failed for a different reason. A tunnel running beneath the channel was technically possible, but came with a price tag roughly 3 times higher than any alternative under consideration. A tall, fixed bridge high enough to let sailboats pass beneath it would have required disruptive, extensive construction directly through the surrounding landscape, and simply building a brand new, more modern drawbridge would have solved nothing fundamental, because boats and cars would still be forced to take turns crossing the exact same physical space, the very problem causing all the delays in the first place. The genuinely unconventional solution that eventually won approval was an aqueduct, essentially a water bridge, a structure that would let boats sail directly over the top of a sealed road tunnel running underneath the lakebed, and the engineering logic behind it traces back over 2,200 years to Archimedes, whose principle of buoyancy proves that a boat floating on the surface of a lake adds precisely 0 additional structural weight to whatever lies beneath that lake, meaning A, road tunnels sealed beneath the water would never have to bear any additional load no matter how many boats sailed directly above it. When engineers formally presented this water bridge concept to the Dutch government, it took only 3 meetings before the plan received official approval, and remarkably, this genuinely unconventional aqueduct solution turned out to be the single cheapest option among everything under serious consideration. Cheaper even than simply building a new conventional drawbridge, while the tunnel alternative that had been ruled out earlier would have cost roughly 3 times as much to build, meaning the strangest sounding idea on the table was, by a clear financial margin, also the most sensible one, and once the decision was finalized in 1998, the old drawbridge kept right on lifting for boat traffic, exactly as it always had, while engineers worked to eventually replace it completely. Construction officially began in the spring of 1998, with site fencing erected and heavy cranes arriving at a lake that, at that point, had absolutely no indication of the transformation about to happen along its shoreline. Before a single foundation pile was ever driven into the ground, engineering crews carried out extensive site investigation work, measuring water and soil depth across the entire planned crossing and mapping the underlying ground conditions down to individual centimeters of precision, and the very first core sample pulled from beneath the lakebed revealed soft gray silt, a discovery that immediately forced engineers to revise their original foundation design before any real construction work could safely begin. That soft silt behaved almost like a sponge under pressure, squeezing water out the moment any real weight was applied to it, meaning engineers effectively had to build an entire section of road inside a completely dry, artificially created construction zone carved directly out of the middle of an active lake, extending earthen embankments out from both shorelines toward the center of the lake until they eventually met in the middle, gradually shrinking the remaining open water gap day by day as fill material pushed steadily inward from both sides. The very first serious construction problem to emerge involved those same embankments repeatedly sliding, because the soft silt sitting directly beneath the newly placed fill material simply could not hold its shape or support the weight pressing down onto it, and engineers ultimately solved that problem by laying heavy geotextile fabric directly across the lakebed before any fill was placed, a material specifically designed to spread the load evenly across a much wider area. And once that fabric was in position, the sliding problem stopped completely, allowing the two advancing embankments to finally meet cleanly in the middle of the lake, effectively splitting the original open body of water in two and sealing off an isolated work zone roughly 60 days into the overall construction schedule. Inside that sealed-off construction zone, crews began driving steel sheet piles directly through 8 meters of soft lakebed silt, gradually forming a continuous 19-meter tall retaining wall meant to hold back the surrounding lake water indefinitely. But partway through that pile driving process, one particular pile unexpectedly stopped at only 6 meters depth, striking a buried layer of dense sand that had never appeared anywhere in the original soil survey data, forcing crews to switch equipment entirely, bringing in a heavier percussion impact hammer specifically capable of breaking directly through that unexpected sand layer until the pile finally reached its full required depth, resolving the unexpected obstacle before it could seriously delay the broader construction schedule. That very same original 1998 steel retaining wall, driven through 8 meters of soft silt and unexpected sand more than 2 decades ago, remains standing today, still actively holding back the waters of the Veluwemeer Lake 26 years later, without any significant failure or major repair. Once that retaining structure was fully in place, powerful pumps began drawing water out of the enclosed work zone, gradually lowering the water level until the actual lake floor itself became visible for the first time, exposed mud and silt that had not seen open air in centuries, ground that, according to engineers working the site, still held physical traces of centuries of Dutch sailing history buried beneath it, including old boat anchors that crews carefully located and removed one by one before continuing further excavation. Standing inside that pumped-out construction zone, surrounded on every side by the surrounding lake still held back by nothing more than engineered steel walls, more than one worker on site later admitted the sheer strangeness of the situation never fully stopped feeling remarkable. A completely dry construction site, sitting in the exact middle of an active lake. To keep that dry construction zone genuinely stable, engineers installed well points around the entire perimeter of the excavation, actively drawing down groundwater pressure in the surrounding soil. A critical step because, without it, pressurized groundwater beneath the site would have continued forcing its way upward through the exposed lake bed in the form of dangerous soil boils. And once those well points were fully operational, that boiling problem stopped entirely, restoring a genuinely stable, dry working surface for the remainder of construction. By 1999, workers found themselves physically excavating a roadway running 3.5 meters below the original lake surface, meaning at certain points during construction, a worker's head was positioned 3.5 meters below the natural water level of the surrounding lake, separated from that open water by nothing more than the engineered retaining wall standing directly behind them. During excavation, engineers conducted a standard cone penetration test on the exposed base of the excavated trench, and the results came back failing, revealing that the underlying soil in that specific location was simply too soft to safely support the enormous structural load about to be built on top of it, forcing crews to stop, dig out that unsuitable soft material entirely, replace it with properly compacted gravel, and only then retest the ground before continuing. And once the retest finally passed, construction was allowed to continue on solid, verified footing, exactly as the revised design required. One engineer overseeing that phase later summarized the stakes involved with simple clarity. Compacted gravel set directly beneath their feet, while open lake water set directly above their heads. And literally, everything constructed in the narrow space between those two extremes had to perform absolutely perfectly for decades to come. Before any structural concrete could be poured, crews first placed a thin layer of unreinforced blinding concrete purely to create a clean, level, genuinely dry working surface. A layer that carried no structural purpose of its own beyond preparing the ground for the critical waterproofing membrane about to be installed directly on top of it. That waterproofing system ultimately consisted of 2 separate full membrane layers, with every single seam and joint between sections welded not once but twice, because engineers understood that even a single unnoticed pinhole anywhere across that entire membrane surface could eventually allow lake water to slowly flood the finished road running underneath it. During installation, a tracked excavator working nearby accidentally reversed directly over a completed section of that critical waterproof membrane, tearing open a gash roughly 600 millimeters long. though fortunately that exact damage was discovered during routine inspection before any concrete was poured over the top of it, allowing crews to cleanly cut out the damaged section entirely and install a replacement patch extending a full 300 millimeters beyond the torn edge in every direction. A repair that was then flood tested independently and formally signed off before construction was allowed to proceed any further. Throughout the entire structure, engineers maintained extremely precise concrete cover measurements, protecting the embedded steel reinforcement bars, because reinforcement covered by too little surrounding concrete becomes vulnerable to corrosion from moisture, working its way in over time, a slow structural failure that, left unaddressed, would continue getting worse permanently for as long as the structure stood. Major structural concrete pours for the base slab ran for 8 continuous hours without any planned interruption whatsoever, because engineers explained that even a small trapped air pocket forming inside an interrupted pour could later develop into a serious crack running directly through the base slab, a risk simply not worth accepting under any circumstance. At the same time, engineers had to carefully manage the opposite problem, because freshly poured concrete naturally generates significant internal heat as it cures, and in cold Dutch, outdoor air too large. A temperature difference between the warm curing interior and the cooler exterior surface can cause visible surface cracking. And at one specific point during construction, engineers actually measured a crack in the base slab reaching exactly 0.15 millimeters, sitting precisely at the maximum allowable design limit, triggering an urgent evaluation before the team ultimately determined the affected section remained safely within acceptable structural tolerance. Every single completed construction joint throughout the entire structure required individual formal inspection and sign-off before work was permitted to continue past it, because engineers understood that even one single failed joint could eventually allow lake water to slowly seep directly into the finished roadway. Running beneath it, and separately, engineers were equally insistent about precise wall positioning accuracy, because a wall built even slightly out of its designed alignment risked being struck directly by passing boat traffic on every single crossing for as long as the structure remained in operation. Consequences serious enough that construction crews were repeatedly reminded there was simply no acceptable margin for minor positioning error anywhere along the route. During the very first major concrete pour, raising one of the primary retaining walls up a full 4 meters, internal vibrators ran continuously, while site engineers watched the surrounding formwork closely for any sign of unexpected movement. And partway through that specific pour, the formwork actually bowed outward by 12 millimeters. A deviation serious enough that, left uncorrected, would have resulted in a permanently thicker finished wall and a correspondingly narrower usable roadway underneath it. So crews quickly installed additional temporary tie rods directly into the still actively flowing wet concrete. And once those extra rods were secured, the formwork movement stopped completely, ultimately saving that section of wall from a permanent dimensional error. Because concrete curing generally requires a certain minimum ambient temperature to properly set, and overnight temperatures at the site regularly drop to around 6 degrees Celsius, crews wrapped insulating blankets across every freshly poured concrete surface each night, specifically to maintain adequate curing conditions until daylight returned. During the second major wall pour, engineers installed a dedicated PVC water stop strip directly inside the construction joint itself, a component specifically engineered around one simple, well-understood principle in waterproofing engineering: that water pressure will always find its way toward the weakest point in any structure first, typically a joint, meaning a properly installed water stop embedded directly inside that joint intercepts water exactly where it is most likely to try entering, and that exact same water stop strip installed back in 1999 has continued successfully stopping water at that joint every single day since. Constructing the roof section spanning 19 meters across the completed roadway required temporarily supporting the enormous weight of wet poured concrete using 200 separate steel props, each one individually adjusted, to an extremely precise height, because engineers explained that props set even slightly too low would allow the finished roof surface to sag downward, creating low areas where rainwater or lake seepage could eventually pool, risking direct contact and damage from boats passing along the surface above. At one stage during that setup process, engineers discovered that a section of props had settled 18 millimeters lower than their intended design height. A deviation immediately flagged and corrected using precision optical surveying instruments, individually readjusting every single affected prop until the entire system passed a strict 3 millimeter tolerance requirement measured across the full 25 meter span of the structure. Reinforcement steel for the roof section itself had to be placed and tied entirely by crews working from underneath, physically looking upward the entire time to verify every single bar sat at its exact required concrete cover distance before final tying was complete. During the actual roof concrete pour, engineers deliberately fed concrete into the formwork through a single centralized pump specifically positioned to allow the material to spread outward evenly in both directions simultaneously, because an unevenly distributed, asymmetric pour risked tipping the entire temporary support falsework system out of alignment under uneven weight distribution. That critical roof pour ultimately ran for 12 continuous hours, with engineers stationed directly underneath the entire time, closely monitoring dial gauges specifically installed to detect even the smallest unexpected movement anywhere in the supporting falsework structure below. Roughly 7 hours into that critical pour, the primary concrete pump suddenly failed due to a hydraulic seal rupture, and with concrete already beginning to stiffen inside the lines, the risk of an unplanned cold joint forming directly through the middle of the roof structure became immediate and serious, prompting an urgent scramble to bring in a standby backup pump, which ultimately arrived and became fully operational again within 52 minutes, narrowly avoiding the formation of a genuine cold joint by roughly 8 minutes, an outcome engineers later described as remarkably close, given everything at stake in that moment. One engineer later reflected that somewhere within the finished roof structure sits the exact physical seam where that pump failure briefly interrupted the pour, though by every account the completed repair was executed cleanly enough that no visible trace of that near miss can actually be identified anywhere on the finished surface today. Once the roof formwork was finally struck and removed, engineers carrying handheld torches carefully inspected every single centimeter of the newly exposed concrete surface, ultimately identifying a small number of minor surface voids, each one subsequently repaired and formally accepted following individual inspection. The critical upper surface of the completed roof structure, the exact surface that would eventually sit directly beneath the open lake itself, was then vacuum blasted to remove any surface contamination, primed, and finally coated with 2 full separate waterproof membrane layers, a level of care engineers insisted on without exception, given that this single surface would ultimately be responsible for carrying the entire weight and pressure of the lake above it indefinitely. On top of that critical waterproofing system, crews then installed a 50mm thick protective concrete screed layer specifically engineered to shield the delicate waterproof membrane underneath from potential damage caused by passing boat hulls, dropped anchors, or future routine maintenance work conducted directly on the lake bed above. During later quality inspection, a chain drag test performed across that finished screed surface revealed a distinctly hollow sound in 2 separate locations, indicating the screed material had delaminated and separated from the waterproofing layer directly beneath it in those specific spots, prompting crews to cut out and completely remove both affected sections, confirm the underlying waterproof membrane remained fully intact and undamaged, pour fresh replacement screed material into the repaired sections, and finally repeat the chain drag test across the same locations, which then passed cleanly, formally closing out that particular repair. A dedicated drainage system was also built into the structure specifically to safely collect and remove any small amount of water that might eventually find its way past the primary waterproofing system, despite every precaution taken. And remarkably, that drainage system has reportedly collected essentially no water whatsoever across 22 full years of continuous operation since the structure first opened. Inside the completed concrete tunnel box, an ordinary asphalt paving roller was brought in to finish the actual road surface, exactly like any conventional highway project anywhere else in the country, and the finished road surface ultimately matched perfectly with the highway sections leading directly into the tunnel on either side, meaning drivers passing through genuinely feel nothing unusual whatsoever, simply an ordinary road, ordinary asphalt. That happens, quite literally, to have an entire lake sitting directly overhead as its ceiling. Wall-mounted lighting fixtures installed throughout the tunnel section were specifically calibrated to prevent drivers from experiencing sudden, disorienting glare or darkness while transitioning from open daylight into the enclosed tunnel dip. And every single monitoring sensor embedded throughout the finished structure connects directly back to a centralized control system based in Delft, configured so that any detected moisture anywhere inside the structure triggers an automated alarm within 30 seconds of first detection. Dedicated pedestrian walkways were also built along both sides of the finished structure, specifically so visitors could stand directly above the tunnel roadway while a boat sails past at the exact same location, offering the strange, genuinely memorable experience of watching sailboats and cars cross paths in the very same physical space from a completely safe vantage point above. Bright yellow buoys installed on the water clearly mark the official entry point into the boating channel above the tunnel, paired with a visible depth gauge specifically warning any vessel with a draft exceeding 3 meters to turn around immediately rather than attempt the crossing. Before the entire structure could finally open, project inspectors compiled a formal list of 47 separate minor outstanding items still requiring resolution, commonly referred to in construction as snagging items, And once all 47 of those individual issues were fully resolved and formally signed off by inspectors, the project team finally moved forward with actually opening the surrounding channel back up to lake water for the first time. Before that permanent opening, engineers first conducted a rigorous 48-hour water test, deliberately flooding the area above the finished tunnel structure to a full 3 meters of water depth, while engineers stationed throughout the site watched every monitoring instrument closely for any sign of failure. During that critical test, engineers did discover a small but genuinely present damp patch appearing on the finished road surface below, traced specifically to a construction joint along the structure's south wall, where a closer camera inspection subsequently revealed a tiny void. Sitting directly beside the embedded water stop, a small gap where concrete had apparently failed to fully fill in during the original pour. To repair that specific defect, engineers injected specialized polyurethane resin directly into the void under significant pressure, completely filling the gap and fully resealing the compromised joint. And once that repair was complete, the entire affected section was retested again under the same full 3-meter waterhead, this time coming back completely dry. Following that successful repair, engineers additionally ran an extended 72-hour water test, specifically targeting that same previously repaired section, and every single monitoring sensor throughout that extended test period, along with a physical visual inspection of the entire road surface, confirmed the structure remained completely dry throughout, allowing engineers to formally sign off the final water tightness certificate for the entire crossing. One engineer later noted with clear satisfaction that this exact same joint, the one that had initially failed its water test back in 2001, was successfully identified, repaired, and thoroughly retested before the surrounding lake was ever permanently reopened to full water flow. That same engineer later reflected that the entire 30-year saga, from a laughed-off sketch in 1990 to a fully certified watertight crossing, opening at the turn of the millennium, ultimately proved something simple: that the most unconventional solution on the table is not automatically the riskiest one. Sometimes it is simply the one nobody had bothered to seriously calculate yet. When the temporary cofferdam separating the construction zone from the open lake was finally removed for good, lake water flowed directly into the newly formed channel above the finished tunnel structure for the very first time. And by every account, everyone present on site that day simply stopped whatever they were doing and quietly watched the water rise, climbing steadily until it reached its full design depth of 3 meters above the tunnel roof, while the finished road running underneath remained completely reassuringly dry throughout the entire process. Shortly afterward, an ordinary road marking machine drove directly through the completed tunnel section without pausing or slowing down at all, treating the extraordinary structure exactly like any other unremarkable stretch of highway anywhere else in the country. During the very first official boat test conducted above the newly opened crossing, the vessel's skipper reportedly looked straight down at the visible road surface beneath the water, turned silently to the rest of the crew standing on deck, and said absolutely nothing at all, a brief, wordless moment that seemed to capture the sheer strangeness of the entire finished structure better than any technical explanation could. And crew members later recalled that the silence lasted noticeably longer than anyone expected, as if the skipper needed a genuine moment simply to process what he had just sailed directly over. Under the combined weight of heavy trucks passing directly beneath the structure, engineers subsequently measured the maximum vertical deflection occurring in the roof section, directly above the roadway at just 1.2 millimeters, remarkably small when compared against an allowable design limit of 15 full millimeters, confirming the finished roof structure barely moved at all under genuinely heavy real-world traffic loading. Around that same time, 2 separate independent inspection teams, one stationed below inside the tunnel and one positioned above on the water surface, conducted simultaneous structural inspections of the exact same crossing, and both teams ultimately reported the structure had fully passed every required test. In 2002, engineers conducted a dedicated nighttime lighting test, carefully measuring illumination levels throughout the tunnel using a calibrated photometer to confirm every single required lux measurement matched design specification precisely, because engineers were adamant that drivers needed to clearly and immediately perceive the transition from open road into the enclosed tunnel section under every possible lighting and weather condition. Every single pump installed throughout the finished drainage and safety system was individually tested, and every connected alarm system was deliberately triggered under controlled conditions to confirm the central monitoring station in Delft correctly received and acknowledged every single alert transmitted from the site. Once all of that testing was fully complete, crews finished the surrounding landscaping, installed a dedicated public viewing platform specifically positioned to let visitors safely observe the crossing in action, and put up permanent informational signage explaining the unusual structure to curious passers-by, officially marking the beginning of regular public operation for what would come to be known locally as the Aquaduct de Veluwe, A structure so strange, it genuinely required seeing to believe, cars quietly passing. Beneath, boats calmly sailing above, standing directly on open water in the middle of the Netherlands, treated today as something entirely ordinary, a daily commute for thousands of drivers who now barely notice the lake, sitting quietly overhead as they pass through underneath it every single morning. Proof that even the strangest sounding engineering idea can eventually become someone else's completely unremarkable Tuesday.